Bem-vindo, and welcome to lecture 3 of a gentle introduction to Fourier analysis and polytopes. My name is Sinai. I work at IME, University of Sao Paulo, and this is part of the 33rd Colóquio Brasileiro de Matemática. For today, let's see what we have for you. The inverse Fourier transform, very important. The FT remembers everything. It's a complete invariant on the space of polytopes. Let's see, the FT of a compact body is infinitely smooth. Well, all these are very nice properties of the FT that make it a very, very nice choice of operator. These are very common function spaces that we finally have to get used to. A very quick intuitive introduction to Fourier series in dimension 1 and dimension D. So this will be a blaze through 200 years. And finally, the very all-important Poisson summation formula, and we'll prove this rigorously and in detail today. All right, let's get started. So time to talk about some common function spaces. And we want to have a result that have the following flavor. If we only knew that our function f belongs to a certain space of functions, then we would automatically know that f has the following nice properties. And what is that nice function space, and what are those nice properties? So many theorems have that flavor, and we have to see. So first, a space of absolutely integrable functions on Rd, that's defined by this set, the set of all functions such that the integral of the absolute value of the function converges. Very, very natural to want this. It's kind of similar to absolute summability, where the sum of the absolute value of the nth term converges, but it's not exactly the same. Let's see, so that's the L1 space. There's an even nicer space, the L2 space. It's nicer because it has more structure. It's a Hilbert space. We can do linear algebra on it more easily, and we can define an inner product on the L2 space. But in the L1 space, it has less structure. It's gigantic, but very useful as well. Both spaces are necessary. So you might ask, is one contained in the other? Well, they're separate, but there are relations. In fact, the intersection is dense in the L2 space, but we won't get into these subtleties, although they're interesting. L2 is the Hilbert space. L1 is the giant space of absolutely integrable functions. For example, in one dimension, let's take the function 1 over x for x bigger than 1, 0 when x is less than or equal to 1. And we easily see that the integral of the absolute value of x diverges. So it's not in L1. However, it is in L2 of the reals, because the integral of the absolute value squared of the function, it's the integral of 1 over x squared from 1 to infinity, and that converges. And so this shows that L2 of R is not contained in L1 of R. Similarly, you can find many functions such that the reverse containment is not true as well, so one is not contained in the other. It's interesting to see these kinds of examples, and I urge you to try to find your own functions for the other containment, lack of containment. All right, the inverse Fourier transform, bread and butter for the theory. Suppose that both f and its transform are in L1, in other words, absolutely integrable. Then we can start with the Fourier transform and take its Fourier transform and get back to the function f here on the left side. So this is the sometimes called the Fourier inversion formula, or inverse Fourier transform. And this is true in R to the D. It's extremely, extremely useful, obviously. An interesting special case is when x is 0. If you plug in x equals 0, the exponential reduces to 1, and we get the following nice special case that follows immediately, but is a non-trivial identity in many instances. So f of 0 is equal to the integral of f hat of xi over all of space. Let's see. A useful alternate way of writing the Fourier inversion formula is the following. We use the script f also for the Fourier transform for many reasons. When you want to compose the Fourier transform with something, or when you want to write the inverse Fourier transform, f inverse, it's useful to have this alternate notation for the Fourier transform, this capital script f. And so f composed with f of a function is the function at negative x. So f composed with f is almost the identity, but up to this minus sign here. And it follows from the previous Fourier inversion formula, and a moment's thought will reveal this follows immediately. Okay, so let's see what's next. Why does the Fourier transform preserve all the information about a set? Well, suppose we have two sets, two polytopes. And so we have to be a little bit careful. Suppose we have two d-dimensional polytopes closed. All of our polytopes are always closed by assumption, S and T. Then the Fourier transform of S is equal to the Fourier transform of T, if and only if S is equal to T. The assumption that they are equal, the transforms are equal, is including, the assumption includes the assumption that it's true for all C in R to the D. In other words, it's true for all inputs. One direction is trivial. If S is equal to T, obviously the indicator function of S is equal to the indicator function of T, and the Fourier transforms are equal. The other direction, suppose that the Fourier transform of S is equal to the Fourier transform of T, and by that we mean this identity here, then for all C, then we can apply the Fourier transform again to both sides of the latter identity, and by the Fourier inversion formula, F composed with F is essentially the function itself again. I say essentially because we evaluate at minus X, that's all, as opposed to X. And so because the indicator function of S evaluated minus X is equal to the indicator function of T evaluated minus X for all X, that's the same as saying that indicator functions are the same, therefore the sets are the same. So this sounds very convincing until there are some wrinkles. One thing to notice is that the indicative function of a polytope is not L1. So is this really important right now? It is important for the proof, but we'll go into why it's not L1 later. Technically, you have to amend this proof a little bit using a slightly more subtle version of the Fourier inversion formula, but we won't go into that. Just to let you know, there are other versions of Fourier inversion for the L2 space. So therefore it's an outline, but the statement is absolutely true. Okay, so in words, we see that the Fourier transform of a polytope P remembers all the information about P. So it gives us a dictionary between the geometry of P and the analysis of the image. And this dictionary between the geometric data and the analytic data of the polytope is very, very beautiful and very powerful. Such an operator is called a complete invariant for the collection of all polytopes by definition of the words. And we talked about this comment below. So we can go on. How smooth is the Fourier transform of a compact body? Well, infinitely smooth, literally. Let P be a d-dimensional polytope. Then the Fourier transform of P is an entire function of C. When we say entire, we mean in the complex sense, but it's okay. You can replace, if you're not comfortable with entire, you can replace the word entire by just infinitely real smooth. So it has infinitely many real derivatives. Because P is compact, we can safely differentiate under the integral sign. This is a special case of the dominated convergence theorem. And namely, for any coordinate variable C sub k, we have partial ck of the Fourier transform of P is equal to this. We can take the partial inside the integral. And this is sometimes called Feynman's trick of moving the integral under the differentiating under the integral, but in any case. And so the derivative with respect to the exponential, that's easy. Partial ck is equal to minus 2 pi I xk. You just take the partial as if it's e to a real variable. It all works the same way as we mentioned in the first lecture. And so now we can differentiate any number of times with respect to any variable. And so it's infinitely differentiable. And so that's it. That shows that the Fourier transform of a polytope is an infinitely smooth function. So that's very nice. We can do something with that. We will in the future. Periodic functions on the real line. Yeah, what are they? It's always good to start with an example. Let's start with f of x is equal to x squared minus x plus 1/6. Happens to be the second Bernoulli polynomial, so it's good for many things. And we define it to be this polynomial inside the unit interval and 0 outside. Here's a picture. It looks like it's smiling at us, right? So it's 0 outside and this quadratic inside the interval. Let's periodize it. This is not periodic, obviously, but we can periodize it perhaps as follows. So algebraically, we can form the infinite series f of x plus n. In other words, we translate x by every integer n and form the sum. And geometrically, it's just this picture at the top. So we take the graph and move it to the left and the right by all integer translates. And remember, little f was compactly supported on the unit interval, so there's no problem with convergence. And this capital F is now a periodic function of x in the reals with period 1. Now, for periodic functions, we have the magic of Fourier series, assuming some level of continuity or even a little bit more differentiability of the function, but we won't get into these levels. We'll assume it's sufficiently smooth that it has a Fourier series that converges properly. And so, yeah, what are Fourier series? What is that? How do we compute it? So let's see. We need to understand a little bit better Fourier series. What do we mean by Fourier series? We mean exactly this. So f has a Fourier series means that f of x is equal to this infinite sum over all k integers, a sub k, these are called Fourier coefficients, times these exponentials. It's always the same exponentials, e to the pi kx. The thing that changes, of course, are the coefficients. And they're called Fourier coefficients, as we mentioned. And this is what we mean by Fourier series. Sometimes it exists, sometimes it doesn't. We'll just restrict to the cases where it exists. We won't talk about the sufficient conditions for existence. That gets into other things. So let's breeze to 200 years of evolution of Fourier analysis in just a few moments, intuitively. First, we will think of f as an abstract vector and the set of exponentials e to the 2 pi kx as k varies to the integers, also as abstract vectors in some gigantic, humongous vector space called the Hilbert space, in fact, L2 of 0, 1. So there is an inner product we can define on this L2 space. And so let's see what it is. And so the fact that these exponentials form a complete orthonormal basis for this Hilbert space L2 of 0, 1 is a beautiful thing, not too difficult, in fact, but we won't go here in the lectures into the details. I go into the details, some of the details in the book. And so the orthogonality, which we will come back to in the lectures as well, is quite important. And so we will assume for the moment that they are a complete orthonormal set. Okay, so now let's suppose that we can expand a function, periodic function on the reals into such a series. What should be the coefficients a sub k? If we assume just a little bit, maybe a lot of linear algebra, then we have sort of no choice. Let's see what the coefficients have to be. So again, e to the 2 pi I mx over all integers m form a basis by assumption, we assume that theorem. And so let's take the inner product of both sides of this identity, if it exists, with e to the 2 pi I mx. Let's see what happens. Okay, so we take the inner product of the right side with e to the 2 pi I mx. We take the inner product inside because it's linear, but now we assume it's linear for all the infinitely many elements. And so now we use the fact that any two of these basis vectors are orthogonal, as we mentioned, with respect to the inner product, which means that exactly this, that the inner product of any two is equal to 0 unless k equals to m. If k equals m, the inner product is 1. This is what it means in general to have an orthonormal basis. But so we'll assume a lot. We'll assume that it's orthonormal and in fact complete. Everything is cool. And so the inner product of f with this basis vector e to the 2 pi I mx, which is a function, is equal to this series. And we said that this vanishes because they're orthonormal, except when k equals m. And so this infinite series has only one term, the k equal m term. And so we get a sub m down here. And that's it. So we've solved for a sub k. A sub k must have the form where it is the inner product of f with e to the 2 pi I kx. And by definition of the inner product, it's this integral from 0 to 1, f of x against the exponential. But notice that we have a complex conjugate. It's the integral of f of x against the complex conjugate. And so we have a minus sign. And that's really nice. The minus sign gets explained now. We see why it occurs precisely because of the inner product in this Hilbert space. And that's where the Fourier coefficients come from the L2 space, initially anyway. And then later we can always massage things further. And so that's Fourier series in one dimension in a nutshell. Okie dokie. Now, let's see, we can revisit our example of the quadratic with this newly found confidence. So there's our quadratic, it's periodic. We periodize little f, the quadratic, by defining capital F. And here's little f again, just as a reminder. And we have one new little definition, which is extremely useful in number theory, dynamics, many things. The fractional part of x. It's defined to be x minus the integer part. Extremely useful. Using this fractional part of x, for example, the fractional part of 3.141 is 0.141. A moment's thought reveals that this capital F of x, which is the periodized version of little f of x, is equal to the fractional part of x squared minus the fractional part of x plus 1/6. In other words, it's the same quadratic with x replaced by the fractional part of x. Okay, so there we have this newly used notation with a fractional part. And that's, again, the picture, recalling the picture of our periodized function. Now we want to find the Fourier series of this f, capital F, the periodized one. Let's write it out. And as we know from our intuitive approach, that we can find the coefficients as follows. A sub k is the inner product, remember, of the function with the exponential. The function capital F is defined between 0 and 1, and we always integrate on the between 0 and 1 in one dimension for us here. Between 0 and 1, it's exactly the same as this quadratic. So it's x squared minus x plus 1/6. And we integrated by multiplying by this exponential with the minus sign always for the Fourier coefficients. I'll save you the headache of integrating by parts, but after 2 integration by parts, you get this formula. So a sub k is essentially 1/k squared up to this constant. This happens when k is not 0. When k is 0, we can always go back to the definition of a sub k, plug in 0 into the exponential. The exponential reduces to 1, and we have that a sub 0 equals this integral. And it just so happens by coincidence that this is 0, but sometimes a sub 0 will be something else. And those are the Fourier coefficients. Going back altogether, we have that the capital F of x, the periodized function, has this Fourier series where the a sub k's are 1/k squared times the constant, and the a sub 0 was 0, so we omit k equals 0 because we cannot divide by 0, and that's it. And that is the Fourier series for the second periodic Bernoulli polynomial right here above. By definition, that's what it is, and very, very useful in many things. And this is very interesting, very powerful identity all of a sudden that we get. You can try to plug in special cases. For example, you can plug in x equals 0. And if you plug in x equals 0, you'll get something interesting. If you plug in different things, you'll get other things that are interesting. The classical evaluations of the Riemann zeta function and so on. You can get a lot of number theory squeezed out of this. Okay, let's move on for the moment. So Fourier series in R to the D, let's do it fast and loose to get you going quickly. Here we define the unit cube, again, 0, 1 to the d, and the space of square integrable functions on it by the L2 space is defined similarly to L2 of R, but here we restrict the functions to have domain the unit cube instead of all of space. And similar definition of the L2 space. We can similarly measure distance between functions here using a similar inner product, except again, very similar, except instead of integrating over all Euclidean space, we integrate over the unit cube in d dimensions. Analogous to integrating over the unit interval 0 to 1, the unit interval is the one-dimensional cube. Okay, so we continue to think of all these vectors, the complex exponentials being basis vectors. And these are abstract vectors in this big space L2 of the unit cube. Okay, so what about periodic functions? Fair question. What do you mean by periodic? Okay, let's define what we mean. There could be many definitions, but let's stick to f is periodic, f whose domain is the real Euclidean space, d-dimensional Euclidean space. F is periodic if its fundamental period is the unit cube, 0, 1 to the d. And by that we mean that if f of x plus m, forget this if here, f of x plus m is f of x for all m integer vectors and all x in the unit cube. So that is what we mean by a periodic function. Okay, let's see. So what about the Fourier series of periodic functions on Euclidean d-dimensional space? Let's see, periodic here. Again, one could imagine different periods rather than a unit cube. And indeed, that happens if some object tiles by translations, you can have a different periodic kind of three-dimensional object, which is interesting and will happen in the future. But for now, the unit cube suffices. Given any periodic function f, whose domain is the real Euclidean space, d-dimensional, we define its Fourier series similarly. Instead of summing over the integers, now we sum over the full integer lattice, which is by definition z to the d, z cross z cross z cross z d times. And now instead of e to the 2 pi I kx, we have e to the 2 pi k dot x, the inner product of k and x. And again, k is over the integer vectors, and x is any real point in space. And so a periodic function is defined on all of Euclidean space, but it's periodic, which means that it has a fundamental period, fundamental domain, the unit cube. And now, of course, the problem is to find the Fourier coefficients. And similarly to what we did before, we can proceed similarly, and we'll just write down the analogous result. Everything is intuitive. And again, for sufficiently smooth functions. So we assume that the function has sufficiently many derivatives, that the Fourier series exists. And the Fourier coefficients a sub k have, again, this form. This is the inner product of f with the exponential. And so we integrate over the unit cube now in d dimensions. And this is, in a nutshell, being fast and loose. This is the Fourier series of a periodic function on r to the d. Okay. So altogether, so this was from before. All right. So the Schwartz space of functions is next. First, we define another useful function space, the space of rapidly decreasing functions. So what is a rapidly decreasing function? A Schwartz function, f, whose domain is R, is defined as an infinitely smooth function on the reals that satisfies the following growth conditions. For every integer ak, positive integers or 0, the kth derivative of a function times an arbitrary power of x, x to the a, is bounded on the reals. Another way of saying it is that both f of x and all of its derivatives decay more rapidly than any polynomial over the whole reals. So these are called rapidly decaying functions. They decay, both f and all its derivatives decay faster than any polynomial. So for example, the Gaussians, which we'll see in a second, are Schwartz functions. Similarly, we can define Schwartz functions in d-dimensional space. We don't have to, it's not very difficult. If you take all partial derivatives of the function f of x and multiply it by any positive power of x's or non-negative, that stays bounded. Similar definition. Again, it means that the function, multivariable function, decays faster at infinity than any polynomial. In fact, decays faster everywhere than any polynomial. The collection of all Schwartz functions is always called a Schwartz space after the amazing mathematician Laurent Schwartz, who really developed the theory very, very far. And in particular, he developed generalized functions. We won't get into generalized functions, but very, very useful theory, extremely useful, in fact, which formalized and made rigorous the Dirac delta function and Dirac's approach to quantum mechanics. The Schwartz space is called capital S of R to the D after Laurent Schwartz. And here's an interesting lemma. I urge you to try to prove it without the isometric property, but the Fourier transform maps the Schwartz space one-to-one onto itself, in fact, isometrically. But without the isometry condition or conclusion, it's still not too bad to try to prove this in R1, let's say. And so it's very nice. The Schwartz space is kind of perfectly suited for the Fourier transform. All right, Gaussians. Here's a nice family of Gaussians in d dimensions. And the 1 over t to the d over 2 is just a normalizing factor. But the meat here is that it's e to the minus pi over t times the norm x squared. In one dimension, it's e to the minus pi x squared. And these t's form a parameter to give us a sequence of Gaussians. So let's see. These Gaussians played a very, very important role for us to the development of the whole theory. They're Schwartz functions for any positive t. They have the following two nice properties. The Fourier transform of the Gaussian is another Gaussian. Notice that the minus pi over t in the exponent gets flipped to a minus pi times t in the Fourier transform side. That becomes useful later on, as we'll see, for the theta function. But anyway, the second property is that the mass, the total mass of every Gaussian is 1. It means that the area under the curve or the end of the surface is 1. Another way of saying it, the probability distribution functions for any fixed t. Let's visualize what happens. Here's a Gaussian, one-dimensional Gaussian for t equals 1, for t equals 0.5, t equals 0.3, t equals 0.1. And so we see that these Gaussians get more and more concentrated near the origin. The peak approaches infinity. In fact, they're approaching the Dirac delta function, which is a distribution, not a function. But it's interesting that these Gaussians are, the family of Gaussians are approaching this kind of pointed infinity while maintaining a mass of 1. And so we will use these Gaussians extensively later. We'll use them after we learn about convolutions to study solid angles, extensions of angles to higher dimensions. And so let's see what's next. So Poisson summation, finally, the Poisson summation formula. The Poisson summation formula says the following. We'll have several versions. The first version is, let's assume f is a Schwartz function. Then we have this marvelous identity between sum of f over the integers and the sum of the Fourier transform over the integer vectors, I should say, and the sum of the Fourier transform over the integer vectors, integer lattice, integer vectors. There is this exponential, but if you set the x to be 0, you get this more pleasing symmetric form that summation f of n over the integer lattice is equal to summation f hat of xi over the integer lattice. So there's a perfect symmetric window here between a sum over the domain. Sometimes engineers might say, or physicists might say, the space domain, and the other side of Poisson summation is the frequency domain. We call xi frequency vector frequently. So yeah, so we'll see many applications of this in our course. You might think that the second case doesn't imply the first, but in fact, the second easily implies the first as well. You can translate, for example, by fn by a fixed vector x, and then use the translate lemma that we proved in the first or second lecture. And so using the translate lemma, you get from the second to the first. And we see here that Poisson is speaking Portuguese. É disso que estou falando. That's what I'm talking about. All right, let's see the proof. Let's look at the periodized capital F. Again, very similar to the example we had. We start with little f, we periodize it to form this capital F. And what is the period? Since we're in d dimensions, the period is going to be the unit cube again. Now I'm going to use the open cube. I probably should have used the open cube throughout. In any case, it's periodic with a period as open, half open unit cube as a fundamental domain. And to see that it is periodic, let's prove it. This is the definition again, that capital F of x plus m is capital F of x. Well, capital F of x plus m is this by definition. You replace x here by x plus m. We collect n and m together. We let n plus m equal k, using the fact that the integer lattice plus a fixed integer vector is again the integer lattice. We're translating the group by a member of itself. So we get the group back. You get that this sum is the sum over k in the integer lattice of f of x plus k. In other words, n plus m equals k. Using this identity that we translate the lattice into itself, you get back again to the function itself. And so we recognize this as capital F of x by definition of capital F of x, and that's the proof that capital F is periodic. Now that we have a periodic function on Euclidean space, we invoke that fact that we mentioned intuitively, that it has a Fourier series. Let's write it down and compute it. By the way, because f is a Schwartz function, that intuitive theorem that it has a Fourier series becomes rigorous. It really does have a Fourier series that converges everywhere, absolutely, and so on. So everything becomes rigorous once we invoke the assumption that it's a Schwartz function. So because f is periodic, we have this Fourier series. Let's compute the Fourier coefficients. We know that they have this form, the integral over the cube of f of t against the exponential for each k integer vector. And so let's see what happens if we massage a k a little bit. First, we can plug in capital F of t. Well, the definition of capital F of t is an infinite sum of little f of n plus t over n, integer vectors. And now we stare at this, and there's sort of only one thing to do next, and that suggests, it cries out, right, to flip the integral with the sum. So we flip, and we have to justify it, and the justification is a dominated convergence theorem. The dominated convergence theorem is something we will assume you know, so if you don't, you can review it from real analysis. Very useful thing. And again, the assumption that it's a Schwartz function, that f is a Schwartz function, allows us to employ the dominated convergence theorem and interchange the sum and the integral. So a sub k has this form. This is reviewing from, recapitulating the last line from the last slide. Now we fix an integer vector n in the outer sum, and let's see what happens if we make this change of variable inside the integral. We let n plus t be w, so we get dt is dw, clearly, because little n is fixed, a constant with respect to the measures. And so now this integral becomes, dt becomes dw, t becomes w minus n, right, from this change of variable. And instead of integrating over the unit cube, we're integrating over the unit cube plus n, because as t varies over the unit cube, t plus n varies over the unit cube plus n. Okay, so there we have it. Now we stare at this exponential, and in kind of a beautiful simplification happens, namely, we can break up the exponential in the product of these two exponentials because of the inner product being bilinear. And we notice that e to the 2 pi I n dot k is 1, precisely because n is an integer vector, k is an integer vector, and so it's our old friend again. E to the 2 pi I times an integer is 1. And that's a very nice simplification. Let's use that. To recap, we've massaged ak into this integral, and this exponential became simplified into this one. And now the integrand is the same for each n here. So the sum over the integral becomes, guess what? A single integral over the whole space, using the fact that the unit cube tiles all of space by translations with the integer lattice. This is one of my favorite steps of the proof. We have this tiling phenomena by the unit cube. And so again, we integrate over the unit cube plus any fixed n, but we sum over all n integers. And because the unit cube tiles, this sum of these integrals becomes a single integral over the whole space. And so ak has this form, it becomes a single integral of the whole space, f of w times the exponential. And so, wow, this is the Fourier transform of f. It's almost like magic. But we in fact define the Fourier transform of f to be that, right? However, even if we didn't define the Fourier transform, look what happens. The proof is so beautiful that it just gets born. The Fourier transform gets born out of nowhere. It suggests itself. And so that's it. A sub k is the Fourier transform of little f of k. And now we summarize by, altogether we have capital F was this periodized version, capital F by the theorem of periodic functions that are sufficiently nice, has a Fourier series, multivariable Fourier series. We computed a sub k to be little f hat of k by massaging and tiling, and that's the end of the proof. Not so bad, actually, right? It has some nice elements, beautiful elements. The proof is pretty direct, I think, but incredibly useful. Simple proof, but incredibly useful. Many applications, math, engineering, physics, everything. So the Poisson summation formula is a powerful tool. And here, Professor Fourier is saying, yeah, it looks like Poisson really did some interesting stuff there indeed. So for today, that'll be it. We have some exercises for you here, and ask questions, stay curious, and until next time.